Okay, so on last Thursday, we talked about creating a conceptual model for flow underneath the Kerr Dam. And you guys had decided to try a water balance model. And so we had drawn in map view, what the dam might look like. And I was in the process of trying to draw it in cross section. And the computer died. I suppose we could start doing that again. But this is essentially one way we could approach your first homework problem, which is figure out a conceptual model for calculating water flow underneath the Kerr Dam, or groundwater flow underneath the Kerr Dam. And this water balance model would be one way that we could do that. So if you guys remember, we had said, well, we want to try this water balance method where we looked at this equation, W in minus W out. And we were trying to create the conceptual model that would allow us to solve this equation and figure out what we would do. So this was my map view. So we had Flathead Lake up here. Here's the dam. There's the river. And then we were trying to decide on what this thing looks like in cross section, like how to draw the boundaries of our watershed or our water balance model. So once again, here's the dam cross section. There's the bottom of the dam. The river, here's the riverbed. And the water pours out of here. It's a top spill dam, pours out of the top, and there's the river, right? And we had decided, I think before my drawing went schizophrenic, that it kind of made sense to think about our water balance over some ambiguous rectangle from the dam some distance downstream. And the reason why was we could think about, this being discharge out of the lake and into our box. And this coming out of the box is the river out, right? And then we thought, well, there'd be other sources we had come up with were groundwater discharge in. And we had lateral flow. What other things did we have that I'm not remembering?
Evaporation.
Okay, so we had evaporation. What else?
Precipitation.
Oh, P. Okay. So this one of the key things we did on Thursday, and one of the hardest things in conceptual modeling for any kind of model, is defining the boundary of your box. How do you separate out the piece of the world that you're going to simulate from the rest of the world? And you do that to try and isolate or to figure out how to answer the question you're tasked with. So, you know, if you recall, our question was, you know, how much groundwater flow do we have coming under the dam? And discharging to the river. So for us, it made sense. Well, if we're going to do the water balance, we want to do it in a place where we can sum everything coming in minus everything going out, and we can try and isolate this groundwater flux. All right, so that was why we sort of chose the boundaries that we did. Okay, so let's write the water balance model then. So what's the water balance equation here?
Flux in minus flux out equals to the change in storage. Minus discharge.
Yep. So both Andrew and Boone said, well, the change in storage is equal to everything going in minus everything going out. So I'm going to put everything going in this set of parentheses. So what's going in? What do I got?
Spill water from the dam.
Yeah, so we got Q in. Yep. What else do we got?
Groundwater flow.
UGW. Hang on. Siri's driving me up the freaking wall. Shut up, Siri. I somehow have Siri turned on my computer, and she keeps coming up and trying to answer questions, and I need to turn her off. All right, I think I just did that. I never ask Siri anything anyways. Okay, hopefully Siri won't interrupt my lecture over again. All right, what else is coming in? We got spill in, we got groundwater in. What else is coming into our box? Precip. Okay, what else?
Lateral flow.
Yep, lateral flow. Anything else? I don't think we have anything else. All right, and what's leaving?
Evaporation. Q out.
You got your Q out. Oh yeah, and evaporation.
Okay. So I think that's it, right? All right, so this is essentially what we need for our conceptual model. We've got a model domain. We've got sort of the boundaries. What are our boundaries? We've got the conditions at the boundaries. And we can go ahead and try and solve this equation for QGW. So let me do it I'm just going to do it in a general sense here. let's see, it would be equal to delta S minus Qn minus P minus Q lat plus E plus Q out. I think I did that all right. Okay, so if we're gonna do this water balance, we got some, what we need to measure a lot of stuff, right? So this, now we can get into the part of the world where we simplify it and start making assumptions. So what are some assumptions we can make to make this a more reasonable document?
Well, you could probably simplify it so it doesn't have evaporation or precipitation.
Yeah, I mean, probably this little box is not very long. We haven't actually decided how long it's going to be, but if this isn't very long, then P or E aren't going to be very big. I think, you know, that's reasonable. We could set these equal to 0. Yeah, I mean, again, this we could say that this is changing, but we all say, well, let's do this, you know, look at this in times when the discharge isn't changing a lot. Or again, if it's short, you know, we would expect that there wouldn't be a lot being stored within the river channel itself. So yeah, I mean, okay. I think that's reasonable. What else? I think we could probably say that if delta S is 0, that means it's not a rainstorm, so P is 0, and that, you know, probably Q lat is 0. All right, and so then we get delta GW is Q out minus QN. QGW is Q out minus QN. And that might be, you know, essentially what we get. Okay, I would like to now think about uncertainty, and that's every place we made an assumption. You know, when we made an assumption or when we defined our boundaries. So we may not calculate or catch, depending on how long this thing is. We could have flow paths like this one that's entering the stream downstream of our boundary. Right? So we don't know we're getting all the QGW. We don't know that delta S is equal to 0. We don't know that P and Q lat and E, we don't know that they're equal to 0. We've made assumptions to simplify the world. So when you make those assumptions, the first thing you got to do is think about how does changing or making those assumptions affect my answer? And what do I need to do to account for that uncertainty? All right, so from the very time we start conceptualizing this thing and thinking about how we're simplifying it, we want to think about how those simplifying assumptions might affect our answer. Okay, so, you know, this has a large part of the the BVP solutions. We got a domain of interest, we have boundaries, we define the boundaries on those conditions, and we have a governing equation. It's not quite the same because we're not really looking at a partial differential equation, but it's essentially a conceptual model that would allow us to attack this problem, and we would be able to attempt to calculate the amount of groundwater flow. Okay, so let's now, so we've done this from a water balance model, and I do want to do it. You know, Andrew said he wanted to do a groundwater model, and I want to do a groundwater model of this same problem right now because it makes it easier to think about how we create groundwater models in other settings. And okay, so we have the same idea. We have a map view and we have cross-section view. But one thing I want to say is that, well, and Andrew identified this, if I was to if I had this line that went along a flow path here, this green line, if this line was drawn better and was drawn right down the middle of this thing, then either side of this line, the domain looks the same, right? The river's the same on either side. The lake's the same on the other side, right? So can you guys see the symmetry there? This is a plane of symmetry where on either side of this line, the domain looks like the reflection of the other. Does anybody not know what I mean when I say symmetry? Because this is not an easy concept, but it's an important one. Symmetry is really important. So what it means is if I have symmetry there, I don't need, if I have a plane of symmetry where this side is equal to this side, all right, these two are the same, then I don't need to simulate the domain on both sides. And I can reduce this problem to 2 dimensions. And the only dimension I care about is a cross section that's a plane along my line of symmetry. So in cross section, this top boundary here would be this line of symmetry that we've drawn. Right, that is laying on top of my map view up there. So that's a simplifying assumption I could make here that's reasonable. It's not perfect because in the real world, this thing isn't perfectly symmetric on either side. Like if we went and looked at the real picture, we probably see that this bank had some contours like this and this bank had contours like that. And so reflecting around this line wouldn't actually be the same. There isn't actual symmetry in the world, but it's close enough. It's close enough, or we can think of it as being close enough for now. But the important point is by making that assumption, we've made our first assumption. We made our first assumption that it's symmetric, and we could think about how that lack of true symmetry might affect our answer. Okay, so I'm going to redraw this cross section. So for a groundwater model, all right, let's redraw the cross section. So we have the lake surface here. We got the dam. And we got the river. Here's our lake bed. And at some depth here, So actually, I'm not gonna, so this is what we know. We know that we're gonna say that symmetry means we can do a two-dimensional cross-sectional model. So I've already made my first assumption. Assume 2D cross-section. And this is due to symmetry. And I will say, well, kind of. It's not perfect. All right. So if this is my system, how could I create a groundwater model or a conceptual model of physical groundwater flow underneath the dam? So what would my domain be? Boundary conditions, governing equation. And let's start off with we'll start off with the domain. What would be the domain you guys would pick here?
Well, I would probably think that there is some bedrock underneath, especially from our the lake bottom might be impermeable. You might have some sort of impermeable layer. And so I want to consider the permeable, the permeable rock on top of the non-permeable.
Okay, does that sound reasonable to everyone else?
Yes. Has a constant thickness of the aquifer.
Okay. So we might say, well, down here is this layer of impermeable. Okay, I don't disagree, but I'm going to say, hey, this is assumption number 2. All right, we've already made assumption number 2. This could affect our boundary or our model. Okay, how far upstream and how far downstream should we include? Should we have this thing? How far should I make this thing go upstream and downstream? You guys got any ideas? 100 meters? Why? Okay, so Jarrett wants to do it at 100 meters. Anybody else got another number they like?
Delta X?
Well, what is delta X?
100 meters.
All right, so I'm going to say it's really hard to pick that number. You could just put your finger out there and say, hey, 100 meters. There's no boundary here to decide. I mean, the lake's really long. The natural place might be to like go all the way to the end of the lake. And then how far downstream would you go? So here's a sum. What's that?
Would you want equal distance up and downstream, or is that not really?
Doesn't have to be. Doesn't have to be equal.
I think that's something that you can iteratively test. Like you can start wherever and then see how your model reacts. And if you think you could see how your model reacts, and then change it if it seems like you want to change it.
All right, so I agree. And so I'm gonna say, I'm gonna just say, here's this random boundary layer at this distance that Jarrett tells me 100 meters good. All right, and then I'm gonna say, well, here's another 100 meters. Okay. So now we've got a box. I would say probably the upper bound of the box ought to be the, since we're talking about groundwater, ought to be the ground surface. Now, I have to define a boundary condition on each one of these boundaries. So you guys tell me what they should be. No flow boundaries everywhere?
The two on the upstream side and downstream side.
So you mean like this one here?
Yeah.
Okay, so why would this be a no flow boundary? Like conceptually, physically, why would I make that a no flow boundary? Anybody, like, we gotta have a reason. If we're gonna put one in, we don't just get to say, hey, I think it's a no flow.
I think you would have no flow on the bottom.
Okay,
And then
why would you say it's a no flow on the bottom?
because you got an impermeable layer,
Okay.
bedrock, whatever we're calling it there. And then I would say on the two sides you should have flow. I'd say the only no flow besides the bottom impermeable layer is whatever wherever else the dam is, but right there, it's like not even, it's above our box.
But wouldn't that be a allowing flow outside of our domain? If we had flow on both upstream and downstream sides.
Let me do this. Let's say I think, can we all agree that an impermeable layer would say what about flow across this domain or this boundary here? So impermeable means what would happen for flow trying to move across this domain?
It's negligible.
Yeah, so I think we can say this is a no flow. And now what I want to talk about is, what does no flow mean? It means no flow across a boundary. All right? It doesn't mean that flow can't occur along a boundary. It means it can't cross it. All right, so this guy is not okay. But this guy, flow along the boundary is A-okay. That can occur right along the boundary, but it can't go across it. All right, so I think we can, for this guy, we can say no flow. I agree. All right, let's think about what is something we can say, like, what is a reasonable thing to say about this bound?
You should be able to have flow there. Because you can have groundwater before you hit that boundary, and then I guess we're making the assumption that we're in a homogeneous material, so you can have flow from one side to the other.
Okay, so a boundary that says we can have flow is not a boundary condition. It means, yes, I agree, but I either gotta set the value of that flow, or I can set the value of the head, or I can do a mixture of the two. Those are the things. So what should we do? What do you think we know? What is a reasonable thing to know about the value of the head here? Or the value of the flux here?
You need to know the depth of the water in the lake.
Boone says I need to know the depth of the water of the lake. Okay, what does that do for me?
Because we can calculate the elevation head from the depth.
Okay, so I agree, Boone. And let's think about what's the head right here. What's the head right here at this spot, P1? And let's say I know this elevation. Let's say this elevation is Z lake. I know the elevation of the surface of the lake, Z lake. So what's my head here at this point, P1?
Is equal to the sum of the elevation head and the gravity head.
It's the sum of the pressure head and the elevation head.
Yes, pressure.
Yeah, it's the sum of the pressure head and the elevation head. I agree with that. And I have an easy measurement of that right now. So what is it? What's the head at that point?
It's equal to the depth of the lake.
It's not the depth of the lake. So I got a question.
Impermeable layer, zero mark. The elevation of the lake is your like most time you can get. So the impermeable.
Okay, so Garrett's saying, well, let's set our datum z equals to 0 right here. I agree. Okay. Seems reasonable. Okay, so let me do this. If I stuck let's say I stuck a fictional well and I screened it here inside the lake. What water level would the water rise to inside my well? All right, the elevation of the lake, right? So here's the elevation in my well inside the lake. So what's the head right here inside the lake? What is it? Oh, it's the gravity head, like Boone said, or the elevation head. So let's call that H sub E. And this is H sub P. Okay, if this is Z sub 0 and this is Z lake, what is H sub E and H sub P equal to?
the depth of the aquifer plus the depth of the lake.
I agree.
Hold ahead. You got what you just said.
So HT, I agree, equal to HP plus HE. And I think that's, yeah, probably equal to this plus this, but I have a direct measurement of it. There's a direct measurement of it right on that figure. What is it?
Z lake.
Yes, right? If this is Z equals to 0, I went up HE plus HP, so the head inside the lake is equal to Z lake. Okay, what happens if I put a well right here? What's the head inside this well that comes down right here?
It all stays Z lake.
So anywhere I put well inside this lake, what is the elevation of that? What is the value of the head?
Z lake.
Z lake. All right, so water, a surface water is a constant head condition. All right, so anywhere along this boundary right here, 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 wherever I want to go, the head is always equal to Z lake. All right, so this right here is a constant head boundary condition equal to Z lake. Okay, I think we can say that this boundary condition is pretty straightforward. It's equal, H is equal to Z lake. All right, so let's do it for the river. What about down here on the river? What is the head at a point here? On this boundary condition, on this boundary.
Equals to the depth of the river.
Yeah, what it is the depth of the river. So if this is Z river, then the head here is H equals Z river. Right, because this is a surface water body. The river slopes a little bit. So we could incorporate that slope, but the head at each point here on this surface is equal to the height of the river, of the water in the river above it, right? Elevation of the river above it. Okay, so I've got this boundary, I've got this boundary, and I've got this boundary. I see 1, 2, 3 more boundary sections that we need to deal with. Got this one, and this one. So what about under the dam? What do you think?
You could have your head equal the, I won't put dimension on there, whatever the depth of the sediment is.
Why would the head go to the depth of the sediment right here?
I'm assuming that's a impermeable dam.
Oh, so why would I can't, if it's an impermeable dam, I would say, I don't know 2/10 of fuck all about the head. But what do I know? If you're saying it's impermeable, what is a reasonable boundary? If it's impermeable, what do I know about flow across this boundary?
There is none.
Ah, okay, so we might say this is another no flow. All right, there's no flux across that boundary. Okay. Still don't know what to do with these side boundaries. Is there anything here that says no, there should be no groundwater flow across this boundary? Do we have any reason to think that that's true? What do you think?
It is groundwater flow. In reality, but it's a model.
So let's think a bit about what happens at this boundary. Okay, so we said, all right, if I came right here and measured on this corner, right, what's the value of the head right here?
Z lake.
Z lake, I agree. And so now let's think a bit, well, what happens if I took a reading right here? What is the condition here?
Also, Z lake.
Why do you think it's Z lake?
You drill the well right there. I'm assuming it's technically not aquifer, so your water level will go up to the as basically your water table. So you get that.
So we just have the cost of that boundary.
So I think that one way to deal with this would be a constant head boundary. It's probably not quite right. And here's the reason why. What that says is, what constant head boundary condition right here means is that there's no downward vertical movement along this. Because the head here is the same as this, the head here is the same as this. It means water will not flow this way. All right, so unless we're a long ways away from the dam, I think that's probably okay, but it's not quite right, but I think that's reasonable. It's a reasonable assumption to say, hey, we don't think that the head is very different from the surface and as we go down. Okay, so similarly, by the same reasoning, so we might say H is equal to Z lake. H is equal to Z lake. All right, so we've got a domain, not lake. Sorry, what should this be here? Not
Z river.
Yeah. Z river. Oh, Z river.
What's the difference between like constant head boundary and having a no flow boundary?
What a constant head boundary says, so here's an example. If my head in here was higher than Z lake, just as an example, for whatever reason, then water could move across this boundary, right? There's no reason why it could. Now, there's nothing here in here unless we like injected water that would cause that. And so actually what you're gonna get here is this is essentially gonna become a no flow boundary. But you can, actually if the head, well, that's not true, it's not true. It's not necessarily a no flow boundary. What probably will happen if we were to model this, we would have a head here that's less than Z lake. And if that's the case, which way will water move across this boundary? If the head at this point is less than Z lake, so here the head Z lake, and here it's less than Z lake, which way will water move? Yeah, it'll move into our domain. So what a constant head does is say, hey, there's this infinite source of water out here that will always keep the water equal to Z lake, and it can flow into our domain. It's an infinite saucer sink. You can think of it like that way. And the head on the boundary will always be equal to Z lake. And similarly here, if we have a head here that's greater than Z river, it can go out here. Okay. So there's some issues here. If this is our conceptual model, if we said, hey, this is a reasonable boundary condition here, and if this is our conceptual model, look at this. I can have groundwater flow. I could have a groundwater flow path, a hypothetical groundwater flow path that flows underneath the dam, and I'm never gonna calculate what it is. Or I would never, let's not say that. My groundwater flow model would allow me to calculate it. I can just look at flux across this plane. But my water balance model that assumed that all the water would discharge into my river wouldn't calculate it. Right? So this groundwater model we might use this groundwater model to say, hey, our water balance model could miss a significant portion of our groundwater discharge, because I could have this flow path conceivably that would never discharge into the river that we wouldn't see, at least over this domain. All right, so we got boundaries, we got boundary conditions. All right, so we got a domain. Check. We got BCs. Check. What about a governing equation? What do you think? What's the right governing equation here? What's the right groundwater flow equation?
We use the total head equation, like a velocity head combined with gravity head, pressure head.
Yeah, so Boone says we want a total head, and I agree. Completely agree. What do you think is a reasonable form of the groundwater flow equation for this scenario?
I'd say you probably have a homogeneous material, and so it's going to be. Well, first, sorry, I want to look at we have like a plane, we have our cross section, our longitudinal section, and so it's 2D.
Okay.
Because we flow in the X direction or to the right, and we're looking at groundwater going under the dam. So we have our second direction going up or down.
So XZ, I agree with that.
Here.
Okay, 2D, XZ, what else? What else do you think we could say about this? I'm not willing to go to homogeneous yet. I mean, why would we say it's homogeneous?
I think at some point we'd said it's gravel and sand, so, but there could be other stuff in there that it's unknown.
Yeah, we can make this assumption if we want at some point, but that's a big assumption. Okay, but there's other things we can do here. 2D, I agree with. What other things might we say here? Let me ask you this. Do you think this is a confined or an unconfined aquifer?
Unconfined.
Okay. Why is it unconfined?
Because the upper boundary is not an impermeable layer.
Okay, so let me ask you this. I agree. Okay, so this is a tricky thing. The aquifer does not have a confining unit as its upper boundary. But why, what is different about the unconfined aquifer equation? What was the main, and this would be more for Garrett and Andrew who've taken my groundwater class. What were the main differences between a confined and unconfined aquifer that made a lot of and the unconfined aquifer?
That's the parameter.
Right, there was an extra head parameter. Why? Why is there this extra head parameter? Let me ask you this, what, in an unconfined aquifer, what did the head map?
That was the water table.
Right, and it's the upper boundary of the aquifer, right? The water table is the upper boundary of the aquifer. What's the upper boundary of this aquifer?
It's a known water level. We can just go and take a measurement.
Yeah, it's fully saturated. The thickness of the aquifer never changes. Now, if we drained this whole Lake Flathead or drained the river dry, we could have a different scenario. But as long as the lake remains filled and the Flathead River runs, all right, the boundary, the thickness of this aquifer stays the same, all right? And the head is above the top of the aquifer. So we never drain the aquifer. The head is always above the top. So what kind of aquifer is it?
Confined.
It's a confined aquifer. Here's another way to think about it. Why was storage different in an unconfined aquifer than a confined aquifer?
Compression.
No, they both have compression. What's different in an unconfined aquifer from a confined aquifer? When I drop the head in an unconfined aquifer, why is that different from dropping the head in a confined aquifer? So, right, so when I drop the head in an unconfined aquifer, I drop the water table. That means I drain pore space, right? In a confined aquifer, I never drain pore space. The head is always above the surface of my aquifer. So I'm never draining water completely out of the pore space. I reduce the pressure, but I never drain the pore space. So this always stays saturated. Right? So this is a confined aquifer. It always, the head's above the surface. It never drains. It's always saturated. And it's constant thickness. Or better than constant thickness, the thickness of the aquifer doesn't change with the head. Thickness of the aquifer is independent of the head measurement. Okay, so this is a confined aquifer, 2D confined aquifer. What else can we say about it?
Steady state flow.
So Boone's willing to go steady state flow. What would that mean, Boone? Why would it be steady state?
The heat doesn't change with respect to time.
And so I think, you know, that's the definition of steady state. I agree, but why would you make that assumption here? Why would you say, hey, I don't think the head is changing with respect to time in this system? Like, what assumption are we saying or making? Okay, so exactly, it means that our boundary conditions are not changing. And is that a reasonable thing? Yeah, this lake, I don't know, it does fluctuate. The river fluctuates less. But we could make that assumption, Boone, and we could make it. So let's start off by, I think confined aquifer is right, 2D, XZ is right, and then we can decide whether we want to make steady state or homogeneous assumptions. So for only these two, my PDE looks like this, SS, EHDT. I haven't made the assumption of steady state. All right, so I'm going to have ahead with time, D, dx, kx, dh, dx. K is inside the spatial derivative, and I put the subscript x here, so I haven't made any assumptions on homogeneity or isotropy. And then d, dy, dy, dh, dy. All right, so we could then make this secondary set of assumptions. All right, and then we would go down to this equation. Oh no. Hang on, before this ruins everything. And I lose a lot of work. I gotta figure out what to do. I'm gonna quit. Okay. All right, hopefully this works now. Let me share my screen again. Boone, you were on the in space, and now you're you're mixing in the studio, huh?
Yes.
Yeah, good.
I mean, radio station. What is your background? Where is that? It's like
It's on
Missoula?
top of Mount Sentinel,
Oh, it's,
just outside campus here. Okay, so if I make these two other assumptions, steady state, so 0, and I can take k out of the spatial derivative. I haven't assumed anything about isotropy, so I'll keep kx and ky. All right, let's say I assumed isotropy, then if I did that, I could get rid of k altogether. And then I would end up with Laplace's equation in 2 dimensions. All right, what's important to realize is each one of these steps, this guy and this guy, those are more assumptions. And you got to justify them, and you got to think about how they add uncertainty. Right, and change your answer. Okay, so we've got a domain, we got boundary conditions, we got a PDE. The last thing we need is if this is our PDE, do I need initial conditions? So if my PDE is star, do I need initial conditions? So Jarrett says no. Why, Jarrett? That doesn't even make sense to say initial conditions. They're not changing with time. So we don't need them. If they're double star, what would you say? So if this is my governing equation, do I need initial conditions? So Jared's nodding his head. Why do I need initial conditions if I'm using double star? Yeah, things are heads changing with time. I better figure out where they start. So we won't go there, but you know, you need initial conditions if you have a transient problem. And then you got to decide what are reasonable transient conditions to start with. All right, and then finally, we need to think about parameters. So we would need kx. Let's see. Actually, let's talk about this. Parameters. What parameters do I need if I make these assumptions and single star is my partial differential equation? What parameters do I need?
All you need is head measurements.
Okay, but this is an important thing. So H, head here, and X or Y, these are variables in your equation. Variables are things that vary. Parameters are things that control the way that the variables behave. All right, so in this equation up here, I got variables H, T, X, Y, and I got parameters SS, KX, KY. Those are the parameters. Those control how my variables respond. So do I have any parameters if I am using single star?
Oh.
No, thank God. That's why we do all this abstraction. None. I don't even need to worry about coming up with them. It doesn't matter. Kind of crazy to think about. But for double star, what parameters do I have?
Specific storage, kx, ky.
And in fact, I'm gonna say that we need to know specific storage for every location. And that actually doesn't make sense to have Y here since we're only in 2D. We need to know KX at all points, X and Z. And we need to know KY and X and Z. All right, and here is where we might say things like, how do we, if we need to know KX at every point in this domain. So we need to know for each one of this XY or XZ points, I need to know K, X, I need to know K, Z, and I need to know SS. And I need to know it for each one of these points. So a big part of what we do is figure out how we can do that. And one way might be to take Andrew's tact and say, well, this is all one kind of layer. It's all sand and gravel. So I can say that KX and KY are the same everywhere. All right. But we have to figure this out. So we're going to look at layering of the geology, natural ways to interpolate between measurements, layering and structure of subsurface. And field measurements. That's what allows us to determine these parameters. That's how we're going to come up with estimates for these. Okay, so this is essentially homework problem number 1. Derive a conceptual model for groundwater flow under the Kerr Dam. We've done it 2 different ways. One, a water balance method. The second, a groundwater flow model. All right. Each one, we gathered all the ingredients we needed to sort of abstract the problem, simplify it into a conceptual model that would allow us to answer the question of how much groundwater flow goes under the dam. So what I would like, for you guys to turn in on these problems, these conceptual model problems, would be something like, okay, here's my abstraction of the process or of the geometry. This is why we chose it. We assumed 2D cross-section because of symmetry. It needs to have the domains, why you chose those domains. All right, those boundaries. And then you need to have the boundary conditions. All right, the boundary conditions should be justified. All right, well, the head at the top here is better be equal to the lake. Impermeable boundary, generally pretty easy to justify, no flux on that boundary. The harder ones to justify are these guys here. So domain BCs, the PDE that you're going to use, there is no right or wrong PDE. Well, there's wrong ones. There's definitely wrong ones. If you were to use, a PDE that wasn't for groundwater flow, that'd be totally wrong. But most importantly is to think about which PDE encapsulates the most important processes for you to answer your question. All right. And then, we could either go with this sort of PDE, or we could make some more assumptions and get to a much simpler PDE. All right. Then you also need the initial conditions and some way you would think about parameters and developing parameters. So the important point is at the end of this conceptual model building, you've got everything you need to solve the boundary value problem and to build a numerical model. All right, and from this, we can build a numerical model and answer this question. All right, but this is the basis of it. And at each point where we made all these decisions, like this is 100 meters long, well, we need to think about how that decision changes our answer, all right, and potentially could. So yeah, this could be something we could test. We made a decision right here, a conscious decision. This was 100 meters. We more or less pulled that out of thin air. So one thing we might want to do when we make a numerical model is change the domain boundaries and see how much that changes our answer. Could be that doesn't matter, you know, as long as we're greater than 100 meters or greater than 50 meters, it doesn't matter. We're going to calculate the same flow under. All right, but each one of these assumptions we want to remember, and we want to think about addressing the effect of that on answering our question. We can do that by changing we can change sort of the permeability structures and the parameters that control it. We can change the processes that we consider, whether it's steady state or transient. So there's a lot of things that we can change as long as we remember what assumptions we've made. All right, I'm going to stop the recording and stop sharing.